Yeah. In like a second. Stuff came out. Stuff was stuck to the toothpick. Okay, just gotta get my.
So tired of diarrhea.
All right. Arrange the camera in a different way.
Open at that live stream.
Seeing.
I don't think anyone's gonna join. If anyone's gonna join, it's probably gonna be like a troll person, like, hey, I'm one of your classmates, Rachel. I don't have a classmate named Rachel. Oh, that's a very common name.
I like how you're making up a whole story about Daddy live stream troll.
You know what a troll is?
Yeah, it's a person who instigates people online for fun.
Once Trump said, we do a good trolling. Like, you face people until like doing bad stuff and be like, you got trolled. Like, just, they're secretly doing and leading them
Yeah.
which is bad. Really pretty bad. Pretty bad. But there's also trolling, which is like telling them that they got trolled. You got trolled.
You might want to check again.
What?
You might want to check to see. Done.
I took it out.
Oh, okay.
They cook very fast. So I knew it would be done momentarily. Thank you.
Okay. I can be heard, but I want my computer to be close. Ooh, we've got somebody. I can't believe it. I'm just gonna wait for well, actually, if you're gonna stay here, then I may as well just get started. So if you could maybe try to stop the dishes procedure for a little bit. Thanks. Okay, so I started before, but I was going over this to nobody, so I will just briefly review what I did. Not too much, as you can see. So the first thing we got to do is write a balanced equation for magnesium reacting with oxygen to form magnesium oxide. So I just got magnesium solid here because it's metal plus oxygen, magnesium oxide, balanced. Okay, so for 2 here, identify a metal in the same period as magnesium that does not form a basic oxide. So please remember, metallic oxides make basic solutions. Non-metal oxides make acids. So aluminum and silicon are the 2 options here, but because silicon is a metalloid, it has to be aluminum. Aluminum, when you react aluminum oxide with water, it'll make some basic oxides and some acidic oxides, and so it kind of neutralizes out. All right, so down here, we've got some experimental data. It says we're going to carry out with a crucible and lid, and the following data was recorded. So we have the empty crucible and lid, the mass of the crucible with our reactant before heating, and then the mass of the crucible with our product after heating. So first thing it wants to know is have you do is calculate the amount of magnesium in moles that was used. So I have mass data here. The mass before heating is what contained my magnesium, so I just have to subtract away the mass from the lid. Don't worry about the uncertainties. Those will come into play in part 2. So my mass of my crucible and my lid is 53.726 minus the mass with empty is 47.372, and that's going to equal 6.354 grams. We need the number of moles though, so I'm just going to multiply it by the molar mass of magnesium, and that's going to give me 0.2 0.2614 moles, and that's our first calculation. All right, next we have to determine the percentage uncertainty. Percentage uncertainty is just the uncertainty over the measurement. So in this case, it'll be the mass. Now it wants the percent uncertainty of the mass of the product. So now what we're going to do is just subtract the mass after heating with the mass before heating, because that'll tell us the mass of our product. So 56. Could you leave that on, Punks, for the... Thanks. 56.941 minus 53.726. And that's going to equal 3.215 grams. Now the uncertainty is 0.001. So the uncertainty is just going to go over the measurement. And it's going to be equal to 3.11 times 10 to the minus fourth. We don't have to multiply by 100 here because when it's percent uncertainty, it's just uncertainty over the measurement. All right, so moving right along. Assume the reaction in A1 is the only one occurring and goes to completion, but some of the product has been lost from the crucible. Deduce the percent yield of magnesium oxide in the crucible. So it wants to know what our percent yield was. Percent yield is our experimental value over the theoretical value. We have the experimental value. It's right down on the other page here, 3.215 grams. We just need to get the theoretical. So we know how many moles of magnesium we started with from part I. So we have 0.2614 moles of magnesium. So I just got to do a standard Stoich problem. So first it's going to be the molar ratio between magnesium and the product. If you look back at the equation, it's 2 moles of magnesium for every 2 moles of magnesium oxide formed. And we want to know the mass that formed. So 1 mole of magnesium oxide has a molar mass of 40.31 grams. I'm going to put that on silent. Hold on, somebody's just asking. Sorry, I don't mean to respond. All right, so anyways, when you do the calculation there, you're going to get 10.54 grams. That's our theoretical yield. So our experimental is 3.215 divided by our theoretical, which is 10.54 times 100 will give us a percent yield of 30.50%. By the way, feel free if you want to leave any questions in the chat. I will try to check and answer. I believe all that's open. All right, it says when magnesium is burnt in air, some of it reacts with nitrogen to form magnesium nitride. According to this equation, evaluate whether this, rather than the loss of product, could explain the yield found in part B. So the first thing I want to say here is magnesium nitride is Mg3N2. That's more than twice as massive as magnesium oxide. So of course some magnesium nitride will be formed, but if the main source of the error were the formation of magnesium nitride, then we would actually expect our percent yield to be greater than 100. By the way, I'm just going to use this test that I already made here for the things that I would have to write out just to save time. So since magnesium nitride is more massive, that should cause the percent error to be greater than 100%. Now, again, I don't have a mark scheme. I'm not an examiner, so my answers may or may not be wrong. You can actually look down here. I actually made an edit. So for part II, it says suggest an explanation other than the product being lost from the crucible or reacting with nitrogen that could explain the yield. So my initial answer was some magnesium oxide would be carried away with excess O2 that's rising from the crucible. I saw this really cool video once where a guy reacted sodium and chlorine gas, and over the reaction flask, he had like a mesh filled with popcorn. So the product of sodium reacting with chlorine is table salt, and all those fumes going through the popcorn infused the popcorn with a perfect saltiness. That's what I originally said thinking of that, but it says it suggests an explanation other than the product being lost from the crucible. So that couldn't be it. The only other thing I could think of to cause the percent to be well under 100% was that not all of the magnesium was reacted. If not all the magnesium was reacted, it wouldn't have picked up mass from the oxygen. So that's the best thing I can come up with there. All right, so on the next page, I will be flipping to that test frequently. I'm probably just going to do the math stuff actually on the paper itself. All right, so blah, 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 blah. Calculate the coefficients that balance the equation. All right, so the first thing I see here is 3 magnesium, so I'm going to put a 3 in front of magnesium hydroxide. I have 2 in front of nitrogen, so I'll put a 2 in front of ammonia. That's going to give me 6 total hydroxide ions. So I'm going to go ahead and put, let me just double check what I did before. Yeah, a 6 in front of water to make sure that worked. I think it's going to be balanced now. So I got 3 magnesium here, 3 magnesium there. That would make the coefficient 1. 2 nitrogen there, 2 nitrogen there. 12 hydrogen here. Well, we got 6 there and 6 there for a grand total of 12, and 6 oxygens from the hydroxide ions. All right, next it says ammonia is added to water that contains a few drops of an indicator. Identify an indicator that would change color using section 21 of the data booklet. So that just basically tells us what our acid-base indicators are. I know that ammonia is a weak base. It's got a pKb of around 4.75. So I'm going to want to find an indicator that would change about in that range. Now, because ammonia, is a weak base, it's going to have a slightly basic pH in your solution. So I would say something like phenol red or phenolphthalein for part 2 here. I said phenol red just because it's easier to spell. All right, so next, determining the oxidation state of nitrogen in 2 compounds. In magnesium nitride, that is an ionic compound, so nitrogen will take its expected ionic charge of -3. In ammonia, remember, hydrogen is always +1, so that means nitrogen here must also be -3. They want it to make you doubt yourself by having the same answer twice, but that's what it is. All right, so part 4, deduce giving reasons whether the reaction of magnesium nitride with water is an acid-base reaction, a redox reaction, neither, or both. So first of all, this is an example of an acid-base reaction. If you look at the equation up above, nitrogen or nitride ions in the magnesium nitride will be given hydrogen by water in order to make ammonia. So that means there must be an acid-base reaction here. And the reasoning I gave was that nitrogen receives hydrogen from water, and also magnesium nitride hydrolyzes water to form H+. So I would consider both of those valid reasons for why this is acid-base. I said it was not redox because even though the hydrogen or the nitrogen gains hydrogen, which would technically be reduction, there's no change in oxidation numbers of any of the compounds in there. If you actually look at each one, all the oxidation numbers stay the same. So I would say no to redox. All right, most nitride ions, let me zoom in as far as I can here with my camera. They're nitrogen 14 with the 3- charge. So state the number of subatomic particles. Protons come from the atomic number. Atomic number of nitrogen is 7. Neutrons are added to protons to get the mass number. Since that's 14, there must be 7 neutrons. In the neutral atom, protons and electrons are equal. Since this is a 3- charge, it means nitrogen gains 3 electrons. So we would have 10 total. Next, some nitride ions are N15 3-. State the term that describes a relationship between N14 and N15. Well, if there's both nitrogen, they have the same number of protons, but different numbers of neutrons. So those are what we call isotopes. I have a feeling a lot of kids are going to kick themselves with that because they thought it was going to be harder than it was. Next, the nitride ion and the magnesium ion are isoelectronic. That means they have the same number of electrons. Determine, giving a reason, which has the greater ionic radius. So here I said the nitride ion would. The negative ion will always be bigger than the positive ion. Since they're isoelectronic, they have the same number of electrons, but magnesium has more protons in the nucleus, increasing its nuclear pull, if you will, reducing the size. This next question down here was kind of obnoxious. Hang on, adjust my camera. I'm not a boomer, but I sometimes appear like one. All right, so suggest giving a reason whether magnesium or nitrogen would have the greater sixth ionization energy. So actually, let me pull out my periodic table here to go through this one. All right, so here's magnesium. If magnesium has 6 ionization energies, that means it's lost 6 electrons. So when it loses 1, 2, 3, 4, 5, 6, it will have the same electron configuration as carbon. For nitrogen, if it loses 1, 2, 3, 4, 5, 6, it would have the same electron configuration as hydrogen. Since we know ionization energy decreases going down a group, that means that nitrogen would have to have the lower ionization energy or higher ionization energy, excuse me, because the magnesium 6 ion would have more shielding than the nitrogen 6 ion. If you can hear my son in the background, I apologize. All right, so next. All right, suggest 2 reasons why atoms are no longer regarded as the indivisible units of matter. I would first talk about the discovery of protons, neutrons, and electrons. Those were essentially discovered by J.J. Thomson, Ernest Rutherford, and Niels Bohr. The other thing I would say, which kind of requires some physics knowledge, is the standard model of particle physics. The standard model has showed us that there are things called leptons, like neutrinos and electrons. There's also protons, and neutrons themselves are made up of smaller particles called quarks, etc. So, I mean, again, this is not the mark scheme. These are just my own answers. Who knows if I'm right or not? I would definitely get a 7, but I probably wouldn't get every mark. All right, so for the next question, they want you to state the bonding type in 3 different substances and describe how valence electrons would produce those bonds. So magnesium is a metal, so its bonding type would be metallic bonding. I'm just going to bring over the definitions here so you don't have to watch me write a bunch of stuff. All right, so metallic bonding is a lattice of cations that are attracted to a sea of delocalized valence electrons. That's really just the definition of metallic bonding. Oxygen molecules are held together with covalent bonding. And in this case, 2 pair of valence electrons are shared between oxygen atoms. Of course, there is that double bond between the 2 oxygen atoms. I think if you just said electrons are shared between them, that would be fine. And magnesium oxide is an ionic compound, and that's defined as electrostatic attraction, just positive and negative being attracted to each other between the magnesium and the oxide ions via a transfer of electrons. Hopefully, me going over this is making you feel better and not worse about how you did. It wasn't the hardest paper, but there was some tough stuff on it, that's for sure. Also, magnesium is a reactive metal that's often found in alloys. Suggests an experiment that shows that magnesium is more reactive than zinc, giving the observation that would confirm this. Remember, if one element is more reactive than the other element, it will replace the other element as an ion. So if an element reacts with a metal reacts with the metallic ion, if it's more reactive, it will replace it. So the thing we could do is just add solid magnesium to a solution of zinc chloride. If the magnesium was more reactive, then you should see solid zinc precipitating out of that reaction. I know a popular reaction chemistry teachers do is putting aluminum foil in copper 2 chloride. It's very similar to that. And welcome to whoever joined here. It's nice to have you. All right, so magnesium is sometimes used as a sacrificial anode to protect steel from corrosion. Calculate the standard potential of a cell formed by magnesium and steel half cells. Use section 24 of the data booklet and assume steel has the standard electrode potential of iron. So here is our table 24. The first thing we have to figure out is which element is going to be oxidized and which one's going to be reduced. remember the element that's higher in the activity series, higher in the table, will be the one that's oxidized. So there's magnesium. There's iron down there. So magnesium will be oxidized and iron will be reduced. All we have to do here is to calculate the overall voltage for the cell, we just take the reduction process, which will be negative 0.45, and subtract away the oxidation, which is minus negative 2.37. When you punch this into your calculator, you get 1.92 volts. That's one of those things that's really easy, but you have to know how to do it in order to make it easy. Next, it says calculate the free energy change, delta G, in kilojoules of the cell reaction using section 1 and 2 of the data booklet. So if it's redox, if it's a voltaic cell, the equation we use is delta G equals negative NFE theta. So here we just have to plug in the values. The number of electrons transferred here will be 2 because we're going from iron 2 to iron and from magnesium to magnesium 2. So that will be negative 2 times Faraday's constant, which is in section 2 of the data booklet, 9.65 times 10 to the 4th, times the voltage we just calculated up here, which is 1.92. And that's going to give us delta G as negative 371,000 joules. Be careful, it's got to be in kilojoules. So it's kind of annoying because voltage is just joules per coulomb. So when you plug into this equation, your answer will automatically be in joules. Since you were asked for kilojoules, we just divide by 1,000. So that will equal negative 371 kilojoules. All right, next, the cell causes the we're about halfway done, by the way. We're a little bit further than halfway done, so hold tight. We'll be finished soon. The cell causes the electrolytic reduction of water. State the half equation. You could work out the equation, or you could just look at the data booklet. This is the equation here for the reduction of water to form hydrogen. So what that'll be is water forming hydrogen gas. When you take the H away from water, it leaves behind OH minus. To balance, I'm going to put a 2 in front of water and a 2 in front of hydroxide. I got a total charge on my product side of 2 minus, so I have to add 2 electrons on the other side. So again, you could either work it out or just get it from the data booklet if you're aware of the fact that it's in there. All right, here, a graph of the volume of gas was produced by reacting magnesium with a large excess of 1 molar hydrochloric acid. That's going to come into play a little bit later on. It says, use the graph to deduce the dependence of the reaction rate on the amount of magnesium. So this graph is very telling to me because it looks like it increases at a constant slope. Remember, the slope of the curve tells us what the rate is. So because the slope is constant, that means the rate is remaining constant. As time goes on, the amount of magnesium will decrease. So you would expect the rate of the reaction to decrease as time goes on. I mean, we've seen that a lot with curves that look like that. Since this one is straight and then levels off, that tells me that there is no effect of magnesium. Next, it says the reaction is first order with respect to HCl. Calculate the time taken in seconds for half of the magnesium to dissolve when the HCl is 0.5 molar. So we were originally at 1 molar and we cut the concentration in half. Well, first order means if we cut the concentration in half, the rate is cut in half. So it looks to me like we formed all of the product in 400 seconds. So it took us 200 seconds to form half of the product. So if we half the rate, it would take us twice the amount of time. So that would take 400 seconds. Next, carbonates will also react with HCl, and rate can be determined by graphing the mass loss. Suggests why this is less suitable for the reaction of magnesium with hydrochloric acid, or HCl. The reason why is because hydrogen is 22 times lighter than carbon dioxide. So unless you have a super precise balance, you're not going to measure a huge mass loss. So you can see the mess I made on my paper here. H2 gas is just too light to measure a change in mass. Ammonia produced by the Born-Haber, I'm losing control of my camera, the Born-Haber-Bosch process, which involves this equilibrium. Percentage of ammonia at equilibrium under various conditions is shown. So we got temperature, pressure, and yield here. Deduce the expression for Kc. So that's pretty easy here. It's just going to be products raised to the power of their coefficients over reactants raised to the power of their coefficients. So in the numerator, I have concentration of ammonia squared. In the denominator, I have concentration of N2 times the concentration of H2 cubed. There we go. Next, state how the use of a catalyst affects the position at equilibrium. Hopefully you know that a catalyst does not affect the position of equilibrium because, sure, it lowers activation energy, but it lowers the activation energy of both the forward and the reverse reactions equally. What's with the waste of paper, Ivy? Come on. All right, with reference to the reaction quotient, explain why the percentage yield increases as the pressure is increased at constant temperature. All right, so for pressure increase, we have to look at the equation. They got 4 moles of gas over here. We got 2 moles of gas over there. So I would expect as you increase pressure to produce more product. So what I actually wrote here on mine, boom, is there are more moles of N2 and H2 are reactants than moles of NH3. So increasing pressure will shift toward the product, ammonia. Now, I didn't know how to really connect it to the reaction quotient. So I just said the initial reaction quotient must be less than K since we had to move, increasing pressure moves it toward the formation of products. That's all I could really come up with. That's one of those ones where I probably would lose a mark. I'm not really sure, to be honest. One factor affecting the position of equilibrium is the enthalpy change of the reaction. So determine the enthalpy change in kilojoules using section 11. Section 11 is bond enthalpy data. When it's bond enthalpy, we're going to be calculating delta H theta by the sum of the enthalpies of the bonds broken minus the sum of the enthalpies of the bonds formed. So delta H theta here will be, just to rewrite the equation here so you can actually see it, N2 plus 3H2 reversible with 2 NH3. I'm going to break a nitrogen molecule apart. The coefficient is 1, so it's just 1 nitrogen-nitrogen triple bond plus 3 moles of hydrogen-hydrogen bonds. That's it for my reactants. And I'm going to subtract away 6 times the nitrogen-hydrogen bond, 6 times because each 1 mole of ammonia has 3 moles of nitrogen-hydrogen bonds, so 2 moles have 6. Now it's just a matter of replacing my symbols here with numbers. So nitrogen triple bond is 945 plus 3 times 436 for the hydrogen-hydrogen single minus 6 times the nitrogen-hydrogen, which is 391. When you plug all these values in, you're going to get negative 93.0 kilojoules. Sorry, the negative sign is outside the box there. So outline why data in B1 may differ when using enthalpy of formation data. They ask this question all the time. Formation data are specific to each compound. Bond enthalpies are averages of multiple compounds, so the bond enthalpies are often less accurate. Demonstrate that your answer to B1 is consistent with the effect of an increase in temperature on the percentage yield as shown in the graph. So we got negative enthalpy change. That means we expect the reaction to be exothermic. If you look back at the graph here, it shows that as we decrease temperature, we increase yield. So if heat is over here, increasing temperature would cause it to shift that way. So that makes sense. What I wrote in mine was as temperature increases, yield decreases. This is expected because delta H is negative or the reaction is exothermic. Boom, boom, boom. Oops, hang on. I flipped it the wrong way. The standard free energy change, delta G, for this process is negative 33 kilojoules at 298 Kelvin. State giving a reason whether the reaction is spontaneous or not. Yes, it's spontaneous, and the reason why is just because delta G is negative. Calculate the value of the equilibrium constant at 298 using sections 1 and 2. When you turn to section 1, the only equation that connects delta G with our rate constant is delta G is negative RT times the natural log of the rate constant. So if we're going to calculate rate constant, first thing I'll do is just rearrange this equation here. So it's going to be natural log of K is equal to negative delta G theta over RT. And now it's just a matter of plugging in the values. We're told up here that delta G is negative 33 kilojoules divided by R. So R is 8.31. That's our gas constant. But remember, it's joules per Kelvin mole. So I have to plug in the kilojoules version by dividing by 1,000. That probably tripped up a lot of kids. And then times the temperature, which is 298. When you plug in, what you get there is 13.3. But remember, that's the natural log of K. It's not K. So in order to solve for K, I have to take E and raise it to the negative 13.3, and that gives me 5.97 times 10 to the 5th. Hopefully that's right. I guess I'll find out when I get the mark scheme in October. All right, so calculate the entropy change in joules per mole Kelvin at 298. So we calculated delta H over here. We were given delta G over here. So the equation we're going to use to do this is our famous delta G theta is equal to delta H theta minus T times delta S theta. So I'm just going to rearrange to solve for delta S. It would be just delta G theta minus delta H theta over T all times minus 1. And now I'm just going to plug in the values. It's going to be delta G, which is negative 33.0, minus delta H, which was negative 93.0, divided by the temperature times minus 1, which is negative 298. I got negative 0.201 on my calculator. That's joules, or that's kilojoules, excuse me. We need this in joules. That's 2 questions in a row where they're being cheeky with the units, but then again, that's just the IB. So in kilojoules, delta S theta would be negative 201 in joules. And outline with reference to the reaction equation why the sign for entropy makes sense. So the sign is negative. That means entropy is decreasing. Well, if you look back at the equation, which was many, many pages ago, you'll see here we're going from 4 moles of gas to 2, so it makes sense that entropy decreases. All right, state the relationship between ammonium and ammonia in terms of the Bronsted-Lowry theory. Those are what we call conjugate acid-base pairs. It's a conjugate pair. You can see they only differ from each other by 1 hydrogen, which is what the definition of conjugate acid-base pair is. Determine the concentration in moles of the solution formed when 900 cubic centimeters of ammonia, which is a gas, at 300 Kelvin and 100 kPa is dissolved in water to form 2 liters of solution. Use section 1 and 2 of the data booklet. You may remember a lab you did where you probably use like butane or something, and you determine the molar mass of butane by collecting the gas in a upturned graduated cylinder. So basically what we need here, and if we want to get concentration, we need the number of moles of solute and we need the volume to calculate concentration, well, I'm not given moles. I'm given the volume of the solution, 2 liters, but I'm given a volume, a temperature, and a pressure. So we can find the number of moles using PV equals nRT. Yes? Huh? 15 minutes, probably 10. We're almost done. I'm almost done. It is close to the end. Sorry, my wife is rushing me. Okay, so we got, when we rearrange, it's going to be N equals PV over RT. So pressure is 100.0 times the volume, which was 900.0, divided by R. We can just use the 8.31 for this problem, times the temperature, which was 300. That gives you 36.10 moles. Divide the moles by the volume of the solution, and we get 18.1 molar, or mole per cubic decimeter. That's a tough one. Usually they would ask a question like that on paper 3, but there was no paper 3 this year, so they asked it here. Calculate the concentration of hydroxide in ammonia with a pH of 9.3. Well, remember, concentration of hydroxide ions is just 10 to the minus POH. So if the pH is 9.3, then my POH is what, 4.7. So 10 to the minus 4.7 equals 2.0 times 10 to the minus 5. This next one was a toughie for sure. A lot of these acid-base ones are tough. It tells us to use section 21. What section 21 is going to tell us is that the pKb for ammonia is equal to 4.75. So I know the Kb for this reaction, when you take ammonia and combine it with water, it forms an equilibrium with hydroxide and ammonium ions. So if I write the K expression, it's just going to be concentration of hydroxide times concentration of ammonium divided by concentration of ammonia. Well, if I want to get Kb, I just do 10 to the minus 4.75. So I'm just going to rearrange to solve for concentration of ammonia, and that would just be, I guess I'll write it out, OH minus times NH4 plus divided by Kb. We calculated concentration of hydroxide up here. Because it's 1 to 1 in the dissociation, that means we also have 2.0 times 10 to the minus 5 for the concentration of ammonia. So it's just going to be 2 times 10 to the minus 5th squared divided by 10 to the minus 4.75, which is 1.85 times 10 to the minus 5. When you plug it all in, you get the concentration of ammonia is equal to 2.2 times 10 to the minus 5. You could also evaluate this answer. Since ammonia is a weak base, it's barely going to dissociate. So we had a concentration of 2.2 times 10 to the minus 5, and hydroxide is 2.0 times 10 to the minus 5. So the answer makes sense. All right. An aqueous solution containing a high concentration of both ammonia and ammonium acts as an acid-base buffer. Referring to this equilibrium, outline why adding a small volume of a strong acid would leave the pH of the buffer solution almost unchanged. So adding acid, since hydrogen ions are a reactant, adding an acid will push it toward the formation of products. So as you add acid, the excess ammonia will react to make the ammonium ion. If we add base here, then that will reduce the concentration of hydrogen ions as it neutralizes to make water. So that would force the equilibrium back the other way. I really hate explaining buffer action, but it is what it is. All right, so magnesium salts form slightly acidic solutions. Comment on the role of Mg plus here in forming the magnesium OH plus ion in acid-base terms. So our hydroxide ion looks like this. When it forms with the magnesium ion, the base donates a lone pair of electrons. So magnesium, in this case, will be acting as a Lewis acid. It's acting as a Lewis acid because it accepts a pair of electrons from the hydroxide ion. And the hydroxide ion, unsurprisingly, is acting as a Lewis base. All right, so this is a question about this complex. It says magnesium is not regarded as a transition metal. Contrast magnesium with manganese in terms of one characteristic chemical property of transition metals other than complex ion formation. So the complex ion formation would explain how color is produced. So really, I'm going to use ionization energy. Ionization energy. That's certainly a chemical property. Now the difference for magnesium, I'm just going to put up what I wrote here. So, successive ionization energies, because magnesium will have large jumps in between its ionization energies, because after losing 2 electrons, magnesium ions will have a noble gas electron configuration. So you'll expect to see those ionization energies jump hugely, but in transition metals, there's very small changes in ionization energy as you go from the first to the second to the third to the fourth and so forth. So because they have a more gradual change, that is kind of one of the things that makes them transition metals. It allows them to have multiple oxidation states. State the name of compound B. So longest chain is 3 carbons. That puts a methyl group on carbon 2 and a hydroxyl group on carbon 3. So that compound is called 2-methyl-propan-2-ol. It then says compound A and B are both liquids at room temperature and pressure. Identify the strongest intermolecular forces between molecules of compound A. So propanone is a polar molecule. It actually has a trigonal planar shape with the oxygen up there, pulling electron density to make it partially negative. But it can't form hydrogen bonds because there's no hydrogen bonds to that oxygen. So the strongest will be dipole-dipole interaction or dipole-induced dipole. It then wants the number of sigma and pi bonds in compound A. All my tests are kind of marked up here now, I'm sorry. So the first bond to form between 2 atoms will be, oh my lordy, I got this wrong. I'll have to redo it for you now. That's good, I just realized, because there's also bonds between carbon and hydrogen. So each single bond is just a sigma bond, and the double bond is 1 sigma and 1 pi. So here I have 3, 6, 7, 8, 9 sigma bonds and 1 pi bond in the double bond. Oops, I'm gonna have to tell my students about that. See how I told you I'm not gonna get every mark. I'm gonna make mistakes like that. Deduce the hybridization around the central atom in carbon A. In compound A, there's 3 domains, so that is an sp2 hybridized molecular orbital. Identify the compound B that exists as optical isomers. If you're going to exist as optical isomers, you have to have a chiral carbon. In order for the carbon to be considered chiral, it has to be bonded to 4 different groups of atoms or groups of atoms. So if you have an asymmetrical secondary molecule like butanol, I see that this carbon here is bonded to a methyl group, an ethyl group, a hydroxyl group, and a hydrogen. So butanol would have optical activity because it has a chiral carbon. Life goes on in my house. No, it's fine. It's fine. All right. So here is compound B. It wants to know a structural formula for the alkene required to make it. This is the one that says we have a big house. So if the hydroxyl group bonds to this carbon, then this carbon must have been involved in the double bond. So this one must have been as well. So I'm going to have a double bond between 2 carbons. We're going to have 2 hydrogens at the end, and I have to account for these 2 methyl groups. So the thing coming off on that end would be 2 methyl groups. So that would be our alkene. Explain why the reaction produces more of the tertiary than it does the primary. That's because a tertiary Carbocation is more stable. A tertiary alcohol is also more stable than primary. That's why we can't oxidize it. You could also say the tertiary carbocation is more stable. So Markov-Nikov's rule will apply here. Deduce the structural formula of the repeating unit. So when we deduce the structural formula of the repeating unit, we just break the double bond, and everything bonded to it is our repeating unit. So it's going to be 2 carbons bonded together. In parentheses, this one is bonded to, sorry, you can't see what I'm doing, is bonded to 2 H's, and this one is bonded to 2 methyl groups. So again, if you look at the main compound, 2 hydrogens on 1 carbon, 2 methyl groups on the other. So that's fine. Deduce what can be observed when compound B is warmed. Compound B is a tertiary alcohol, so no reaction will occur. Iodomethane is used to prepare that thing. It can also be converted into methanol. Identify the type. Here we have a halogenoalkane reacting with a nucleophile, so that is nucleophilic substitution. In fact, it will be an SN1 reaction because it's a primary halogenoalkane. So outline the requirements for a collision to be successful. 2 requirements: they have to collide in the correct orientation, and you have to have sufficient kinetic energy to satisfy the activation energy. I'm kind of going through this quickly because I'm being rushed. So I'll save it as a video for a couple days in case you want to go back and look at stuff. Because I got all this stuff here. I don't have a table out there. All right, so outline the, oh wait, I already did that one. We have literally a page and a half to go. We're almost done. All right, so explain the mechanism using curly arrows to represent the movement of electron pairs. So this is going to be our SN1 mechanism. So it's iodomethane. We have to show the wedge and dash notation for this molecule. I like to put my leaving group kind of in that spot. Everything here is just a hydrogen. So the first thing that's going to happen is our nucleophile will attack. So you have to draw a curly arrow going from the electrons to the opposite side carbon of the iodine. That causes the leaving group to leave. That sets up our transition state, which will have partial bonds to our attacking nucleophile and our leaving group. Everything else here will stay the same, but as you may remember, something is going to change in our products. This all has a 1- charge. And then the final product, we will get that inversion of position. So my hydroxyl group will be there. The bond that was dashed was on the right side, so now it'll be on the left side. The bond, or that was wedged, dashed, and the bonds that was wedged switches places, and the hydrogen's up there. Don't forget to show your leaving group or you lose a mark there. Really, that's just kind of memorize the picture. That's what organic chemistry is. The polarity of the carbon-halogen bond facilitates attack by the hydroxide ion. Outline giving a reason how bond polarity changes going down group 17. Remember that as we go down the group, the strength of those bonds will decrease because the electronegativity of those halogens decreases going down a group. All right, here we just want the electron configuration of nitrogen. Remember, it's going to be 1s2, 2s2, 2p3. So 1s2, 2s2, 2p3. Don't forget to follow Hund's rule and distribute those one at a time. Deduce a Lewis structure for nitric acid. I got to be honest, I had to Google this one. I didn't even know it. If your teacher doesn't know it, then it's probably not that important. It is 2 marks, but it is what it is. All right, so explain the relative lengths of the 3 bonds. So even if you weren't able to draw this, I would just go ahead and assume that there was a double and a single bond. So the double bond is shorter than the nitrogen-oxygen single bond, but each nitrogen-oxygen single bond will be equal length. So the reason why the double bond is shorter is because that bond contains more electrons. And that bond exists because the nuclei of the bonded atoms have a mutual attraction to those shared electrons. The more electrons they are, the greater that attraction, so the closer they are together. All right, last bit. Explain, there we go, never mind, flipping. State a technique used to determine the lengths of bonds. It's the one we don't have to analyze, but we have to know what it is. X-ray crystallography. Mixture of nitric and sulfuric acid can be used to convert benzene into nitrobenzene. Topic 20. Write an equation for the reaction between the acids to produce the electrophile. So there we're going to take sulfuric acid and mix it with nitric acid. That's a reversible reaction. Now, sulfuric is stronger than nitric. It has a higher Ka value. So it's going to donate a proton to the nitric acid, leaving behind the hydrogen sulfate ion and making this intermediate H2NO3 plus. That intermediate is very unstable, so it will decompose into the nitronium ion and water. Really just memorize the equations. Unfortunately, I hate memorization stuff, but there's plenty of it here. All right, draw the structural formula of the carbocation intermediate produced when this electrophile attacks the benzene ring. So remember, after the nucleophile attacks, it interrupts the aromaticity in benzene. So we show that as a semicircular dotted ring with a plus sign in the middle. We still have the hydrogen attached there, but we also have our nucleophile attached there. And that would be our intermediate. Of course, water will come in, that water actually in the equation will come in and deprotonate that, but leaving behind our nitrobenzene. But that is what we're looking for the intermediate. Deduce the number of signals that you would expect in the NMR of nitrobenzene. So the first thing I'm going to do is just kind of draw the structure of nitrobenzene. I'll draw it with the double bonds that are there, even though they're not really there. So this is a molecule that's symmetrical about that axis. So any mirror image hydrogens are in the same environment. So I got one environment there, two environments there, and three there. So there'd be three signals in the NMR. And there's two in that environment, two in that environment, and one in that environment. So it would be 2 to 2 to 1. That's it. I'm done. I'm done. I'm done. All right. Well, I hope that was helpful. I'll leave this open as a video for a couple days, just in case anybody who said they wanted to come actually comes. I really appreciate you stopping by, because even if it's just for one kid, I'm happy to do it. All right. Well, any questions before I hit the road? All right. I'll take that as a no. Have a great night, and good luck in college.